I'm Riley Mays, and I'm the team lead.
Hi, I'm Richard Holloway, and I'm the procurement lead.
Hi, I'm Jose Navarrete. I'm a mechanical engineer.
Hi, I'm Spence Mraz, and I'm a mechanical engineer.
Hi, I'm Yazid Dajani, and I'm a mechanical engineer.
Hi, my name is Daria Ali, and I'm an industrial engineer.
Hi, my name is Maxwell Harvey, and I am a management engineer.
And we are
Density Matters.
In aluminum recycling, one of the key challenges is the low density of scrap material when it is baled. Loose aluminum scrap often contains a significant amount of airspace, which reduces the efficiency of the remelting process. This leads to increased energy consumption, higher levels of dross formation, and lower overall material recovery. Current baling methods compress the material, but they are limited in how much density they can achieve due to the irregular shapes and stacking behavior of the scrap. As a result, there is a clear need for improved methods that can enhance compaction before or during the baling process. Our project addresses this issue by exploring how pre-processing techniques such as crumpling and shredding can increase the density of aluminum bales and ultimately improve recycling efficiency.
With this problem in mind, we defined a few key objectives for our project. First, we needed to design and build a small-scale baler that can consistently produce uniform bales. Next, we focused on finding ways to increase bale density through processes such as shredding. This changed how tightly packed the material could be. Finally, we needed to understand the bigger picture, so we analyzed how bale density impacts material yield and dross formation during remelting. The overall goal is to not just build a working system, but to also provide insights and design recommendations that can improve industrial baling processes.
So here you can see our full baler system in CAD, which brings together all of the main subsystems into one complete design. Starting with the mechanical side, this includes the compression chamber, the frame, and all of the structural components that handles the loads during operation. This is where the actual bale formation happens. Then we have the hydraulics system, which is what drives the compression process. It uses pressurized fluid to actuate the cylinders, allowing us to apply the high forces needed for both stages of compression. And finally, the electrical system is what controls everything. It powers components like the motor and vibration system and allows us to safely operate the baler through switches and control inputs.
For our engineering approach, we focused on understanding how bale density impacts the overall efficiency of aluminum remelting. The biggest gap we found is that there isn't much published research that isolates density as a single variable. Most existing data is multivariable, process-dependent, and often proprietary, which makes it hard to directly evaluate how density alone affects performance. To address this, we approached the problem from a mass balance perspective. For example, if you input around 15 pounds of aluminum, you might only recover 14 pounds. That loss is a result of dross formation and emissions during the remelt process. This led us to our main hypothesis, that improving bale density will reduce these losses by minimizing oxidation and improving heat transfer during remelting. To evaluate this, we're tracking key performance metrics like yield, dross formation, and the energy required per melt. Since the total mass going into the system is fixed, any improvement in yield directly reflects a reduction in losses, which is what we're trying to optimize. Ultimately, our goal is to establish a clear relationship between bale density and remelting efficiency and provide data that can be validated and potentially applied in industry.
In this part of the video, we're highlighting the key concepts that allow our system to actually achieve high-density bales. The most important feature is our dual-cylinder compression system. What you're seeing here is the hydraulic cylinders extending and retracting, which drives the entire compression process. We designed this as a two-stage system. The first stage applies an initial compression at a lower pressure to compact the loose material and remove large air gaps. Then the second stage applies a much higher pressure to further densify the material and form a solid, uniform bale. This staged approach is important because trying to fully compress loose scrap in a single step isn't very effective. It leads to even unpacking and limits the final density of the bale. In addition to the cylinders, the compression chamber is specifically sized to produce consistent bale dimensions, which helps with repeatability. We also included a hopper system with a vibration motor to help the material settle before compression, and an ejection system that allows the bale to be removed cleanly after it's formed. All these components work together to make sure the system is not only effective, but also consistent and repeatable in its performance.
To validate our design, we performed a series of engineering analysis to make sure the system could safely handle the loads during operation. Starting with the ram heads, we analyzed both the low compression and high compression stages. Each was subjective to its respective face pressure, and the results showed very small displacements and stresses well below the material yield strength. Both designs achieve factors of safety significantly above our requirement of 3, confirming they are structurally sound. We also analyzed the anchor assembly, which is responsible for transferring loads into the frame. The results showed a strong distribution of stress with minimal deformation, again meeting our safety requirements. For the compression chamber, we simulated internal pressures during operation. The analysis confirmed that the chamber can withstand the applied loads while maintaining structural integrity and consistent geometry. Finally, we evaluated the I-beam, which supports the entire system. Even under the full applied loading, the stresses remained well below the yield strength, and the factor of safety was well above the required threshold. Overall, these analyses confirmed that our design is safe, reliable, and capable of performing under the expected operating conditions.
To make sure our systems performs as intended, we established a set of engineering requirements and verified each one through testing and analysis. Starting with electrical constraints, the system is designed to operate using standard wall power, no more than 120 volts and 20 amps, which ensures it's practical and accessible. These requirements were met and verified through inspection. For performance, the system successfully achieved the target bale size of 3 by 3 by 3 inches, and both compression stages meet their required pressures. The first stage reaches approximately 1500 psi, and the second stage reaches just under 4200 psi, both within acceptable margins. We also verified that the hydraulic system operates within its pressure capacity of 3000 psi, ensuring safe and reliable performance. In addition, we included a mechanical indicator to track cylinder displacement, which helps monitor system operation. Some measurement and safety features, like precise mass measurement, emergency stop response time, and guarding, are currently in progress, but have been incorporated into the design. Overall, the system meets all critical performance requirements and is on track to fully satisfy all remaining criteria.
In this section, we're demonstrating the full operation of our aluminum baler. We start by loading the loose aluminum scrap into the hopper. At this stage, the material is irregular and contains a lot of empty space. Next, we turn on the vibration motor. This helps the material settle, redistribute, and allow for smaller pieces to fill in the gaps and improve packing before compression. After a few seconds, we turn the vibration off and allow the material to fully settle into the chamber. Once the material is positioned, we begin the first stage of compression. This initial compression reduces large air pockets and begins forming the shape of the bale. After that, we move into the second stage of compression, where a much higher pressure is applied. This step further compacts the material and creates a dense, uniform bale. Finally, we remove the ejection door and the completed bale is pushed out of the chamber. This process demonstrates how pre-processing and staged compressions work together to significantly improve material packing and overall bale density.
So here are the results of our system. As you can see, we were able to successfully produce a uniform bale with consistent geometry. The material is much more tightly packed compared to the loose scrap, which significantly reduced air gaps. This improvement in packing is largely due to the pre-processing and the two-stage compression process, which work together to increase overall bale density. By increasing density, we expect to see improvements in remelting efficiency, including higher material yield, reduced dross formation, and lower energy required per melt. Overall, these results support our original hypothesis that pre-processing and stage compressions can have a meaningful impact on aluminum recycling performance. Throughout this project, we faced a number of challenges, especially with structural design and making sure all of our subsystems work together smoothly. Integrating the hydraulics, mechanical components, and material handling took multiple design iterations. Overall, this project taught us the importance of testing, adaptability, and refining designs based on the real system behavior. Safety was a major focus in our design. We included features like interlocks on the hopper and the ejection door to prevent operation when the system is open, as well as an emergency stop that cuts both the hydraulics and electrical power. In addition, all pinch points and moving components are properly guarded to ensure safe operation during use. In conclusion, our team successfully developed a lab-scale aluminum baler and demonstrated that pre-processing methods like crumpling can improve bale density. The system produces consistent, testable bales and provides a strong foundation for evaluating remelt performance. Overall, this project shows a practical approach to improve efficiency in aluminum recycling.